As AI accelerates and demands on hardware grow, long-standing assumptions in chip design are being challenged. Now, new research shows larger, specialized chips are outperforming their smaller, cutting-edge counterparts in deep learning. But will this trend continue? Join us as we speak with Michael Davies to discuss Defying More, envisioning the economics of a semiconductor revolution through 12nm specialization.
The field of computer architecture is at this really interesting intersection of the AI revolution, the end of Moore's law, and more recently this semiconductor blockade. And so the purpose of our paper is to try and see how all these things are interacting and look at the role of computer architecture versus the role of technology scaling.
What was observed is that AI accelerators fit into an abstract form called TDCC, or Tiled Decoupled Control and Compute Architecture.
And from this, we were able to develop a high-level model to project deep learning performance for TDCC architectures and see how the relative sizing of different resources and how much is devoted to each of these things, like compute, bandwidth, or wires for moving data, how much each of these affect overall performance for deep learning.
The findings were eye-opening, indicating that Moore's law scaling doesn't translate directly to deep learning gains.
Going from 12nm technology to 3nm, we're seeing substantially lower improvement than what we would expect, around 2.9x projected versus the 8x that you would expect from simple technology scaling. Because of this, 12nm technology combined with architectural specialization can achieve performance in deep learning competitive with 7nm and 5nm designs, while reducing the costs and improving sustainability.
Specialization, regardless of technology, leads to better performance and power efficiency, ultimately translating to less infrastructure needed to serve the same workload.
At the end of the day, if you have a more performant or more power efficient chip, this translates to less e-waste at the end. Now, when you add technology back into the mix, newer nodes have much higher embodied carbon emissions. So if we move 3 nodes from, say, 12nm to 3nm and only get 2 to 3x performance, which is what we were projecting, but the embodied carbon emissions is much higher, we need to be asking ourselves if this is really worth it from an environmental standpoint.
In this time of renewed importance within computer architecture and the rapid advancements of AI, what does the future hold?
The diminishing returns from the continued technology scaling highlight the importance of exploring cost-effective, specialized designs that address the growing computational demands of AI with better energy efficiency and economic viability. And personally, what I'm excited about with all this is using AI as sort of a vehicle to explore more interesting architectural specialization in the future.
Find out more in Defying More, envisioning the economics of a semiconductor revolution through 12nm specialization, a research article in the July 2025 Communications of the ACM.